Hi everyone, I hope you can hear me. So today we will be discussing few questions in computer networks. Okay, so mainly I will be discussing TCP/IP. So I will be discussing, let me just tell you what I will be going to discuss. I am going to discuss TCP and I am going to discuss IP. I am going to discuss DVR protocol. So I will be focusing like our discussion to these three things. So in IP I will be discussing the fragmentation. In IP we will be discussing fragmentation, and in TCP we will be discussing a few questions of TCP and DVR. Okay, DVR is distance vector routing protocol. So let's just start. Suppose that we have this question, and question is saying that consider a source computer S transmitting a file of size 10⁶ bits to a destination computer D. So there is a source computer S that wants to transmit a file to D, and the file is having 10⁶ bits, right? The file size is 10⁶ bits. So let me write it here. The file size is 10⁶ bits, and this S wants to transfer this file to D over a network of two routers. So there are in between there are two routers, R1 and R2, and there are three links. So this is L1, this is L2, this is L3. So this is what it is written here, that L1 connects S to R1, L2 connects R1 to R2, and L3 connects R2 to D. Let each link be of length 100 km. So the length is given that here each link is having 100 kilometers. Similarly, L3 is also 100 km. And then what they have asked, assume the signal travel over each link at the speed of 10⁸ meter per second. So they have given the speed V to be 10⁸ meter per second. And then assume that link bandwidth. So each link is having some bandwidth which is basically 1 Mbps. Let the file be broken down into 1000 packets such that each packet is having size of 1000 bits. See, total size of file is 10⁶ bits, right? 10⁶ bit is total size of file, right? Now they are saying that you can divide this into 1000 files such that each is having 1000 bits. So there are 1000 such files, right? 1000 files such that each is having 1000 bits. Now what they are asking, find the total sum of transmission and propagation delays when you are transmitting this file from S to D. So in these kind of questions, just listen carefully. In these kind of questions, what we are going to do, we are going to just focus on last packet. Okay, so there will be how many packets that you are transmitting from S to D? There are 1000 packets you are transmitting. So let's just focus on only last packet. So let's first transmit all the packets. So if you transmit, let me write it here, transmission time for all packets, what it will be? See, for one packet the transmission time will be length upon bandwidth. So what is length? Length is 1000 bits upon what is bandwidth? Bandwidth is given to be 1 Mbps, which means 1 into 10⁶ bits per second, right? So this is your bandwidth. Now what they've asked? They've asked that like total time. So this is the transmission time for one packet, and if you just multiply with the 1000, which means 10⁻3, then you will be getting transmission time for all the packets. Now which means this will be just 1 second, because everything is in the second. This 10⁶ is 10⁶ like bits per second, because the bandwidth is given to be 1 Mbps, right? So where it is written, the bandwidth, I think they have written somewhere. So bandwidth is given to be 1 Mbps, which means if you just convert that to bits per second, you will be getting 10⁶ bits per second, right? So everything is in second. So that's why my total transmission time is 1 second. Now what they are asking, total time including the propagation time. So once you transmit all the packets, just focus on the last packet. Now tell me how much time last packet will be taking. So let me write it on the next page. Last packet time. Last packet time. How much time last packet will be taking? It will be taking 3 into propagation delay, because there are 3 links on which it needs to travel, 1 2 3, right? So 3 propagation delay it will be taking, and 2 transmission delays. See, 1 transmission from here and 1 transmission from here. So what we are doing, we are transmitting all the packets, and then I am focusing on the last packet only. So if you just focus on the last packet, how much time last packet is taking? Why I am focusing on the last packet? Because by the time last packet is going to deliver to D, then all the packets are automatically going to deliver, right? So by the time last packet going to deliver, then all the packets are automatically going to deliver. So let's just focus on the last packet. So if you just focus on the last packet, then you will say that time that last packet will be taking is 3 into propagation time, because there are 3 links on which it need to propagate, plus 2 into transmission time. Why? Because there are 2 more routers on which it needs to transmit. So how much time it will be taking? Like the propagation time is given to be distance upon velocity. So what is the distance? Just see here, the distance is given to be 100 kilometers, right? So propagation time will be 100 upon speed, and speed is given to be 10 to the power 8 meter per second. So basically you will be getting, this is 100 kilometers, then I have converted that into meter, and then 10 to the power 8 meter per second. So this will be your propagation time. So which means this is 10 to the power 3 into 10 to the power 2, 10 to the power 5, which means 10 to the power minus 3, right? So 10 to the power minus 3 seconds, which means it is just 1 millisecond, right? This is just 1 millisecond, which means the propagation time you are taking is 1 millisecond for 1 link. So for 3 links, since there are 3 links, 1 2 3 links, so you will be taking 3 milliseconds propagation time, plus 2 into transmission time. So how much transmission time you are taking? Just check it. See, the transmission time that we have earlier calculated was 1 second, right? So which means, let me write it in millisecond only. Let me write. So this is 1000 millisecond. So which means you are taking 1000 milliseconds here. 1000 milliseconds. So okay, that is the transmission time for 1000 packets, but just for 1 packet you will be taking 1 millisecond, right? So I am only focusing on the last packet. So that was the transmission time for 1000 packets, but just for the last packet you will be taking 1 millisecond. See, that was for 1000 packets. These are the 1000 packets, that's why you are multiplying by 1000. So that's why you are coming out to be 1000 millisecond is the transmission time for 1000 packets, but just for 1 packet you will be taking 1 millisecond, right? You can just do length upon bandwidth. So if you do that, you will be getting 1 millisecond only. So which means you are getting 5 milliseconds from here. So last packet is taking 5 milliseconds plus transmission time of all packets. Time of all packets, which is 1000 milliseconds. So that's why your answer is 1005, right? See what we are doing. We are we have constructed the network, and then we are saying that total time for this 1000 packets will be the total transmission time for the 1000 packets. Once you have transmitted the 1000 packets, just listen here carefully. Once you have transmitted the 1000 packets, then I am only focusing on the last packet. Then how much time last packet is taking? So that's what we have done here. We have transmitted all 1000 packets, and then I am focusing on the last packet only. Why I am focusing on the last packet? Because by the time the last packet is reaching from S to D, then all packets would have automatically reached, right? By the time last packet is reaching. So that is why I am focusing on the last packet only. Okay, I hope you got it. So that's how we are calculating the total time, which is 1005. Now if you have understood this, then let me know if there is any doubt. Otherwise let me know. Then we are going to solve a next question which is completely based on this. Okay, is this clear? See what we are doing, we are transmitting all the packets, then we are focusing on the last packet. Why? Because by the time last packet is going to reach to destination, then all the packets would have automatically reached, right? So that's what we are doing. Now let's do this question. In a packet switching network, packets are routed from source to destination along a single path having two intermediate nodes. So they are saying there are two intermediate nodes. Let's suppose this is source and this is router 1 intermediate node, this is router 2, this is another intermediate node, and then this is destination. If the message size is 24 bytes, so they are saying they want to transmit 24 bytes, right? if the message size is 24 bytes and each packet contains a header of 3 bytes, so total message size is 24 bytes, and along with that, if you want to like you can divide this this message into number of packets. So these are the 24 bytes that you have, and then you can divide them into number of packets. If you do that, I mean that depends on you, that depends on the question, that depends on you, how you want to optimize. So if you do that, then each packet will be having 3 bytes header. So let's suppose you have divided into number of packets, then one packet will be let's suppose you have divided into 3 packets. So this is 8, 8, 8, right? So there will be 3 packets. Let's suppose, for example, I am just taking, and then you will be having 3 bytes header each, 3 bytes header, 3 bytes header. This is what they are saying. Now they are saying that then the optimum packet size is. So they are asking for the packet size. So basically they are asking in how many packets you are dividing it. So you got the question. So in how many packets you are dividing, such that you like you want to optimize it. Basically you want to optimize the transmission. If you just send this 24 bytes as it is, then if you see, then transmission time will be dominating. Why? Because if you see 24 bytes, then there will be too much transmission time just for one packet, and then very much transmission time here, and then transmission time here, right? So there will be too much of transmission time. So basically, let's suppose if I divide this packet into 10 packets, then what is happening? That let's suppose if I have divided that 24 bytes into 10 packets or 8 packets or anything like that, okay? Then how it is going to solve my problem is like this. See, suppose you have divided into 10 packets, okay? This 24 bytes, okay? Then what we are going to do? There are 10 packets here, 10 packets here, and then when you are transmitting all the, like you need to transmit all the packets. Let's suppose you are transmitting packet, you are transmitting packets, and you are at the, let's suppose 7th packet, you are at the 7th packet you are transmitting. Then what may happen? When you are transmitting the 7th packet, at that time only, maybe this packet, which is maybe the first packet, maybe reached here, right? First packet may reach here, and then you are basically forwarding the first packet from here, right? So basically what I am saying, if you are dividing into number of packets, then it will be useful. Why? Because of pipeline, which means if you are dividing into, let's suppose 10 packets, then by the time you are transmitting the 7th packet, maybe your first packet may have reached here, and you are also forwarding the first packet. But if you have just one packet, let's suppose of 24 bytes, okay? If you have just one packet, let's suppose you have just one packet, then you are basically transmitting this packet here, and then you are not doing any more progress. So basically you want to optimize, you want to check that how many packets should be there, and how many packets you want to divide this this particular packet, right? Yes, Shailesh, we want to divide a packet in such a way that there is no like the packets are not too large or not too small. So that is the question that they are asking. So do you want to solve this question? Anyone? So let's do one thing. Let's suppose that the packet size, let's suppose that they have divided that packet 24 bytes into some number of packets, okay? So let's suppose they have divided like total we are getting k number of packets. This is number of packets, and total we have 24 bytes. Let's suppose each packet is having some bytes. Let's suppose each packet is having x bytes, okay? These are the bytes for each packet of each packet, okay? Then tell me how much total time it will be taking. Total time, how much total time it will be taking? So as I told you earlier, see here, this is source, this is destination, sorry, this is some router, let's suppose R1, and then this is some router, let's suppose R2, and then this is some destination, okay? Now how much total time it will be taking? It will be taking the total time for the transmission of all the packets, as we did in earlier question, right? Transmission of all the packets, plus I will be just focusing on the last packet. So why I am doing it? Because my argument is that if you transmit all the packets, see, you anyway need to have the transmission time of all the packets, and once you transmit all the packets, then I am just focusing on the last packet, and I will say that the time like the moment that last packet is reaching to the destination, then all other packets will have already reached, right? So total time is transmission time of all packets, right, plus last packet time. So how much last packet will take? It will take, see, the last packet has already transmitted from here. It will take 1, 2, 3 propagation time, right? 3 propagation time plus how much transmission it will take? It will take 2 transmission time, right? This is what last packet will be taking. Is this okay to everyone? And what is the transmission time of all the packets? So let's just calculate the transmission time of all the packets. See, each packet is having x bytes of data, right? X byte of data, and there are k packets, which is basically 24 by x. This is how we can calculate this k. Now if you see the question, then they are saying that like if each packet is having x bytes of data, then there has to be 3 bytes of header, which means the total size of one packet, the size of one packet, or let me just write it L, the length of one packet is x plus 3. Is this okay to everyone? The length of one packet is x plus 3. Why? Because each packet is having x bytes of data and 3 bytes of header. That's why length of one packet is x plus 3. And how many packets are there? K packets are there. So the total transmission time of all packets from source, like from source only, right? From source is nothing but length upon bandwidth into k, because there are k packets, and this is the transmission time for one packet. So what is the length? Length is x plus 3, right? Length is x plus 3 upon bandwidth, I don't know, but let's assume it to be bandwidth, and then you will multiply by k. Is this okay to everyone? So this is the total transmission time that you have, right? And then what we do after we get the transmission time, then what we do? See, the total transmission time we are getting is x plus 3 upon bandwidth into k. Then we will focus on the last packet. Now if we just focus on the last packet, this is router 1, this is router 2, this is destination, then how much time extra last packet will be taking? Last packet will be taking 3 propagation times, which means 3 into whatever is the distance. Let's suppose I don't know the distance, and also let's suppose I don't know the velocity. Okay, so 3 propagation times that last packet will be taking, plus how much time it will be taking? 1 and 2 transmission times. So 2 into what is the transmission time of one packet? It is x plus 3 upon bandwidth. So this is the total time that I am taking. Is this okay to everyone or not? This is capital T, which means the total time I am taking, and I want to minimize this time. Okay, I want to choose x such that I want to minimize this time. So basically, let me do one thing. Let me just combine this x quantity. So basically, this is kx plus 3k upon bandwidth, plus this is 2x plus 6 upon bandwidth, right? Plus 3d upon v. This is what we are getting. And now I want to just keep the x together, which means this will be k plus 2x upon bandwidth, and then plus this will be some constant, basically 3k upon bandwidth plus 6 upon bandwidth plus 3d upon bandwidth, 3d upon velocity. So this whole thing is constant with respect to x. Now if you just if you want to optimize this, then what you need to do? You need to differentiate this with respect to x. So is this okay to everyone? Just check if there is any problem here. So I think that is okay, right? So you can just substitute this k. So okay, this k is not constant, you need to substitute this k because it is also in terms of x. This is 24 upon x, right? So you need to substitute the k, which is 24 upon x. So let me go to the next page. It is basically 24 upon x. So this was k plus 2 into x, k plus 2 into x plus 3k upon bandwidth, right? Plus 3k upon bandwidth plus some constant term, and now you can substitute this k to be 24 upon x. If you do that, you will be getting 24 upon x plus 2 into x plus 3 into 24 upon x upon bandwidth. Okay, upon bandwidth I am not writing, or let me write it here, because anyway it will be just going to 0, because if you differentiate then it will go to 0, and plus some constant. This constant is as it is. I have just substituted this k to 24 upon x. Now if you just multiply by the x, you will be getting 24 plus 2x plus 3 into 24, which is 72 upon x, right? Which means you are getting 2x plus 72 upon x. Is this okay to everyone? So 2x plus 72 upon x is the only x quantity. So if you differentiate this with respect to x, then you will be getting 2 minus 72 upon x square equal to 0, right? This is dt upon dx, and this was the t, right? So basically this was 1 upon bandwidth. I mean, everywhere you will be having 1 upon bandwidth. Here also you will be having 1 upon bandwidth, but that bandwidth will go to the 0. So that's why let's not worry about the 1 upon bandwidth, and then you will be having this as 0. Then from here, if you solve, you will be getting x as 6. So 6 is your optimal size, which means if that's the 24 bytes, then you are dividing each into 666, which means how many packets you are dividing? In 4 packets you are dividing, right? You are dividing into 6666, and there are 3 bytes of header also. So this is 3 byte of header, 3 byte of header, 3 byte of header for each of the packet. Then each packet size will be how many bytes? 9 bytes, 9 bytes, right? Each packet size will be 9 bytes. So let's see which option is correct in the packet switching network. So optimal packet size they have asked, so it is 9 bytes. So that's why D answer is D option is correct, right? So I hope that is clear to everyone. Now what we were doing, basically we were just focusing on the last package. See, in both of the question, in this question also we were just focusing on the last packet, and in this question also we were just focusing on the last packet. So the trick, or the useful idea that we have implemented is this: the total time is the total transmission time of all the packets, and then the extra time that is taken by the last packet. Okay, that's how we are solving this question. Now we are getting 9 as packet size, which is optimal. Now let's do this question. Now what they are saying: consider the following statement about the functionality of IP based router. A router does not modify IP packet during the forwarding. So what do you think? A router modify or does not modify the IP packet? So they are asking which one is true. So router obviously modify. Router modifies TTL field at least, right? Router always modify TTL fields. So basically one is not true. Does not modify, not true, which means it modify. So one is false. This is false. What about second? It is not necessary for a router to implement any routing protocol. So yeah, that is true, because router can actually flood the packets. If the packet is coming to the router, then router can actually redirect that packet to any other direction. So it is not necessary, but for the optimization purpose we need to have this, right? So but it is not necessary. So yeah, that is true basically. A router should reassemble IP fragments if MTU of the outgoing link is larger than, okay, so they are saying the router should reassemble if the MTU of the outgoing link is larger, which means suppose here you are getting 2 packets, but here the MTU is very much sufficient. Let's say the MTU is 50,000 bytes, something like that, okay? Suppose 50,000 bytes. Then they are saying the router is going to reassemble. So if you remember the reassembly code or reassembly algorithm, then router never reassemble, right? So that's why this is also false. So which one is true? I think only second is true. So that is why D is answer, right? Yeah, Sandeep, that's very good question. Sandeep is saying that they have not specified the packet of optimal size, but packet of equal size. But since they are just asking for one packet size, see, there are not multiple options first of all, then the optimal packet size. So they are just asking for one packet size. So that's the implicit assumption. But even if you have the different packet size, okay, different packet sizes, then like that will be very complex question, and then in that case also ultimately your answer should be having, like ultimately like you can start with that, okay, the packet size are not same, maybe x1 x2 x3, but ultimately your answer when you find the answer, it will be having x1 equal to x2 equal to x3. Okay, even if you start with the generalized approach of having different packet sizes, but your final answer should be having x1 equal to x2 equal to x3, and that I think that will be very complicated. But anyway, they have asked for the optimal packet size, and there are only one options. There are not multiple options with the commas. So let's do the next question. I hope that is okay to everyone. Now they are saying, in a sliding window ARQ scheme, the transmitter window size is n, which means the sender window is n. So there is a sender, there is a receiver, right? So sender window size is n, capital N, which means there are n packets that you can have in the sender window size, and the receiver window size is m. Receiver is having m packets. I mean, receiver can receive m packets at a time. The minimum number of distinct sequence numbers that you require. So what is the answer? I think you know this, right? If you remember, then suppose WS is your sender window size and WR is your receiver window size, then this should be less than equal to available sequence numbers. So ASN is available sequence numbers, right? So why that is the case? Can anyone tell me why WS plus WR should be less than equal to ASN? So why that is the case? Because let me just give you some justification of that. Suppose that your sequence numbers are 4, which means, or maybe 8 sequence number, 0 1 2 3 4 5 6 7, and then again 0 1 2 3 4 5 6 7, like that. Okay, then again 0 1 2 3, like that you have. Okay, and let's suppose this is your sender, this is your receiver, this is sender, this is receiver. Now suppose, okay, tell me, if there is a 8 sequence number that you have available, then tell me, can you send this as a whole window once to the receiver? Can you send these many packets at a once to receiver? You cannot send. Why? Because receiver is waiting for something, right? Like you do not know, I mean, that does not even matter. Suppose receiver is waiting for 4 packets, or if you are sending these many packets, then let's suppose receiver is also waiting for 10 packets. Okay, so receiver is, let's suppose, also waiting for the 10 packets, and you are sending the 10 packets, suppose. Then what's going to happen? Suppose this 0 1 2 3 4 5 6 7 you are sending, and then you are sending 0 1, right? Suppose that this 0 is lost, okay, and receiver is only getting, or maybe if not lost, then maybe suppose that this 0 is delayed, which means this 0 is getting delivered later and this 0 is getting delivered first. Then receiver has no way to identify that this 0, whatever 0th packet number you have received, this 0 is which one, this 0 or this 0, right? That receiver is waiting here. So basically you cannot send packets which are having the same sequence number, because in this case receiver will not be able to identify. So that is very clear that you cannot send the packets more than 8, right? More than 0 to 7 you cannot send. But my question was that why we cannot send till 7? Okay, so more than 7 is anyway not possible, more than 8 is anyway not possible, but my question is why we cannot send till 7, which means why we are not sending 8 packets at once. So I hope my question is clear to everyone. Why we are not sending 8 packets, okay, and why receiver is not waiting for 8 packets? So this is my question. So let me erase this and let me just explain. Okay, so question is that why sender is not sending all the packets, which are the 8 packets at once, and why receiver is also not waiting for the 8 packets. Suppose this is sender and this is receiver. Now suppose sender send all packets 0 1 2 3 like that till 7. Suppose sender send all the packets, and yes Sandeep, that's correct. So and receiver basically is waiting, let's suppose, for 8 packets only. which means receiver is waiting for 0, 1 till 7. And now these all packets has been received and receiver is sending ACKs. Okay, receiver is sending ACKs. Suppose this is ACK1, this is ACK2, like that. Receiver is sending ACKs. Okay, and now consider a case where this all ACKs are getting lost. You understood the scenario? See, sender is sending all the packets, receiver is receiving all the packets, but when receiver is sending ACKs, these all ACKs are getting lost. Then what will sender think? I mean, there will be a transmission timeout, right? There will be a timeout for every packet at the sender side. So sender will think that, I think that actually maybe all the packets have been lost, right? So sender will again send all the packets, isn't it? Sender will again send all the packets 0 to 7. And these are the retransmission. These are the retransmission. And receiver, since the receiver has already received 0 to 7, receiver is also waiting for 0 to 7, but this is the next 0 receiver is waiting. Next 0, next one receiver is waiting. Not the old. This is the old 0, right? This is the old 0 that sender is sending, but receiver is waiting for new 0 or the next 0, isn't it? Now, when these all packets get transmitted, then receiver will think that, like, receiver has no way to identify whether these packets are duplicate packets or not. So the receiver will think that these packets are new packets, and receiver will happily accept those packets, which is actually wrong. So you're getting what is happening here. Sender is sending some packets, right? And receiver is getting the packets, but ACKs are lost. All ACKs are lost. Then in that case, receiver is waiting for some new packets 0 to 7, new 0 to 7, new 0 to 7. Sender is sending 0 to 7, but those are old 0 to 7, because according to the sender, like, it has to send all the packets because the ACKs are lost, right? So these are old 0 to 7, and receiver is waiting for new 0 to 7, isn't it? Because based on the receiver, it has received all the packets, now it has sent the acknowledgement, now it is waiting for new 0 to 7. Now what will happen in that case? In that case, receiver will erroneously accept this, right? Receiver will think that, okay, these are the new 0 to 7, so receiver will say okay. But this should not happen. That is why whatever sender is sending, right? Whatever sender is sending, if the sender has to resend all those, then the receiver should not be waiting for this old sequence numbers, which means if sender is sending some packets, okay, maybe 3 packets, and receiver is, let's suppose, waiting for 3 packets. I mean, does not matter, 3, 4, 3, 2, 1, like whatever, but let's suppose this receiver is also waiting for the 3 packets or 4 packets, it does not matter. So basically in this case, what will happen? Suppose that ACKs are lost and these sequence numbers are 0, 1, 2, and these all ACKs are lost. Then in this case, let's suppose your total sequence number is 0, 1, 2, 3, 4, 5. Your total sequence number is this. Now once receiver receives 0, 1, 2, it will wait for what? 3, 4, 5. Receiver is waiting for 3, 4, 5. And you are sending what? You are sending 0, 1, 2 again. You are sending 0, 1, 2, and this is the old 0, 1, 2. You are sending 0, 1, 2, and receiver is waiting for 3, 4, 5. Will there be any problem? No, right? Because receiver will easily identify that, okay, these are not the packet receiver is expecting. So basically, even if you have to retransmit all the packets, then there should be enough scope that receiver should be waiting for entirely new window, right? This is the concept that we want to implement. Is this okay to everyone? So even if you have to retransmit all the packets, then also receiver should be waiting for entirely new set of packets. So suppose you have 0, 1, 2, 3, 4, 5, 6, 7 as your sequence number, then again you are repeating your sequence number like that. These are the packets number you have. So if you send 0, 1, 2 at once, then receiver, let's suppose sender and receiver window size is 3 and 3, and then receiver will wait for 3, 4, 5 in the next iteration, right? And that is not a problem, because even if you retransmit 0, 1, 2, then receiver is waiting for 3, 4, 5. That is not a problem. Can you send 0, 1, 2, 3? If you send 0, 1, 2, 3 at once, then receiver will be waiting for 4, 5, 6, 7, right? Next 4 packets, which are 4, 5, 6, 7. So then again there is not a problem, because even if you retransmit 0, 1, 2, 3, then also receiver is waiting for completely new set of packets, which are 4, 5, 6, 7. So even if you have 0, 1, 2, 3 in your sender window, then also no problem, right? Can you send 0, 1, 2, 3, 4 at once? Tell me. If you send 0, 1, 2, 3, 4 once, then receiver will wait for 5 packets, which are, let's suppose, 5, 6, 7, 0, 1, right? Receiver will be waiting for 5, 6, 7, 0, 1. And then once you retransmit, let's suppose you are sending 0, 1, 2, 3, 4, and then these are received, and then all ACKs are lost, okay? ACKs are lost. And then you need to retransmit 0, 1, 2, 3, 4, right? And tell me what receiver is waiting. In this case, receiver is waiting for 5, 6, 7, 0, 1, right? Now, when you send this 0, 1, receiver has no way to identify whether this 0, 1 is old 0, 1 or new 0, 1, right? The receiver is waiting for basically this 0, 1, and you are sending this 0, 1. So receiver has no way to identify whether these 0, 1 are old or new. So that is why whatever you are sending, even if you have to resend it, then receiver should have the enough space. Receiver should be waiting for completely new, different set of sequence numbers, right? So whatever is your available sequence number you have, so let's suppose this is the available sequence number you have, which means let's suppose maybe from 0 to let's suppose 127, anything, okay? Whatever available sequence number you have, then suppose you send this much, let's suppose this is your sender window size, then receiver should be waiting for, then it will be like, it is 0, then again you are repeating, right, to 127. Then receiver should not be waiting for basically any duplicate. So basically receiver should be waiting for either this much only, maybe this much at max. Receiver should not be waiting for this 0 also. If receiver waits for this 0, then there will be a problem, because if you retransmit this 0, receiver has no way to identify whether this 0 is a duplicate 0 or this is a new 0. You got it? So that is why you can say that whatever is your available sequence number, if this is your sender window size, then your receiver window size could be only this, could be only this, could be only this, and could be at max this. So basically your sender window size plus receiver window size cannot exceed your available sequence number. That's why we have this relation in place. Let me know if there is any doubt. Is this okay to everyone? So now let's come back to our question. Now what they are saying, that receiver window size is n, receiver window size is m, and sender window size is n. Then the distinct sequence number that you need. So how many sequence number you need? You need at least m plus n sequence numbers, right? So why I am saying at least? Because see, if there are let's suppose you have far bigger sequence number, let's suppose 2 power 10 sequence numbers, then there is no problem. I just need at least m plus n sequence numbers. Why? Because if sender window size is n, then receiver should be waiting for entirely new m, right? Entirely new m. This m should not be having any sequence number that is overlapping with the numbers from 0 to n, right? 0 to n. I hope that is okay to everyone. So C is the correct answer here. If there is any doubt, then let me know. Okay, if there is no doubt, then let me move to the next question. So yeah, so this is our next question. The maximum window size for the data transmission using the selective reject protocol with n bit frame sequence number. So they are saying maximum window size for the data transmission with the n bit sequence number. So what should be the answer? See, in the selective repeat or selective reject protocol, you have the sequence sender window size and receiver window size are actually same, and if there are n bit sequence number you have, then total sequence numbers are basically 2 power n possible, right? From 0 to 2 power n minus 1. From 0 to 2 power n minus 1, you have 2 power n total sequence number. Available sequence numbers are 2 power n. And then what they are asking? they're asking that maximum window size. So what could be the window size? If these two has to be same, and we know that WR plus WS should be less than or equal to 2 power n, then since these are same, then WR cannot exceed 2 power n by 2, which means 2 power n minus 1. And if they are asking for the maximum, then maximum could be 2 power n, which means this inequality just convert into equality. So this will be WR equal to 2 power n, because they are asking 2 power n minus 1, because they are asking for the maximum. So that is why B is the correct answer, right? Okay, now let's go to this question. They are saying consider three machines M, N and P, and they are having different IP addresses. So M is having some IP address which is 100.10.5.2, and N is having some IP address which is 100.10.5.5, and P is having some IP address which is 100.10.5.6. okay, the subnet mask is set to, so they are saying the subnet mask is 255.255.255.252. so if you remember, then 252 is all ones, 6 ones. This is 6 ones, 1 2 3 4 5 6 and 0 0. Why? Because this is just 3 less than 255, so that's why I have 0 0 in place of 3. So what does this mean? It means they are saying that initial, so if this is the subnet mask, then they are saying that initial these bits plus 6 bits. So if you represent this 2, let me just only write this 2 in the binary, so it will be 1 0, which means 0 0 0 0 and 0 0 1 0, right? And if you write this 5, I think this is 1 0 1, so this is basically 0 0 0 0 0 1 0 1. And if you write this 6, it will be 1 1 0 0 0 0 0 0 1 1 0. So they are saying that initial 26 bits are fixed, this is 24 plus 6, which means 30. So initial 30 bits are fixed, because in initial 30 bits you have ones, so initial 30 bits are fixed. So you can only basically change these bits, these 2 bits, right? Okay, I think that's very easy question. So you can only change these 2 bits. Now they are asking that M, N and P all belongs to the same subnet. So what do you think? Do they all belong to, are they having the same network ID? See, if you just see, then N and P are having basically same network ID. M and P are having 100.10.5 dot something, which is basically 0 0 0 and 0 1, right? But you cannot change this 0 0 or this 0 to something else. So M is belonging to the different network. So that's why you can say that which is the correct option here? N and P are belonging to the same network, same subnet, which means C is the correct option, right? Let me know if there is any doubt here. Okay, so let's do this question. Suppose two hosts have TCP connection to transfer a large file. Which of the following statement is or are false with respect to the TCP connection? So let's read out each option. If the sequence number of a segment is M, okay, so what they are saying that two host uses a TCP connect to transfer a large file. So basically, let's suppose this is A, this is B, and if the sequence number of a segment is M, the sequence number of the subsequent segment is always M plus 1. So what do you think? Is this correct? If you are sending some packet with only M sequence number, okay, they are saying false. So if you are sending a sequence number with M, then the next sequence number will be what? Will it be M plus 1, or depends on the number of bytes you are sending in the first packet? That depends on the number of bytes, right? So that is why this is not correct. So that is why this is false. This is false. What about second? If the estimated round trip time at any given point of time is T, so let's suppose RTT they are calculating, RTT is small t, and then the value of the retransmission timeout is always set to greater than equal to T. So which means that if RTT is just T, sending and receiving this time is just T, then obviously the retransmission timeout should be greater than T, right? Because if it is less than small t, then there will be too much inefficiency. I will be unnecessarily retransmitting every packet. So that is actually true, right? That is true. The size of advertised window never changes during the course of TCP connection. No, at every transmission we advertise some window. If you remember in the congestion control, so at every packet from the receiver we are advertising some window, which means this is false. So it always changes. The number of unacknowledged bytes at the sender is always less than or equal to the advertisement window. Okay, the number of unacknowledged bytes. So what they are saying at the sender side, right? So let me write it here only. So suppose this is your sender window, and in this window, let's suppose these packets are sent, but not acknowledged, but not acked. These packets are sent but not acked, and these packets are about to send. Now what they are saying, the unacknowledged bytes at the sender is always less than or equal to the advertised window. Yes, that is true, right? Why? Because suppose I am advertising that my window size should be 4 KB. Let's suppose this is what I am advertising. Then what sender will do? Sender will send 4 KB, right? If I am saying that send me 4 KB, then what sender will do? Sender will send 4 KB, entirely 4 KB. This 4 KB sender will send. Okay. Then what's going to happen? Sender will wait for the ACK. Wait for ACKs, right? Now suppose that sender has got ACK for some packets. Let's suppose sender has got ACK for initial few packets. Okay, these packets sender has got ACKs. So they are saying that these are the unacknowledged, right? Unacked. So sender has got ACKs for this. Sender has not got ACKs for this. So isn't it these unacknowledgement bytes? Isn't it less than what advertised window is, which is 4 KB? See, this whole thing is 4 KB. And actually, like, this unacknowledgement cannot be greater than 4 KB. Why? Because unacknowledgement is something which I am sending, and I cannot send more than what is being advertised, right? So I cannot send more than what is being advertised. That is always less than or equal to the advertised window. So that's why this is true. So I think 1 and 3 are false. So which means B is correct answer, right? B is the correct option here. I hope that is okay. Now let's go to the next question. Now in this question, what they are saying, this question was asked in 2021, that consider two host P and Q connected through a router R. The maximum transmission unit MTU between P and R is 1500 bytes. So MTU between P, let me use the red color, MTU between P and R is 1500 bytes. And between R and Q is 820 bytes. And between R and Q, MTU is 820 bytes. Okay. A TCP segment of 1400 bytes was transferred from P to Q. So they want to send some TCP segment of size 1400 bytes. They want to send 1400 bytes. So TCP segment means it includes the header, right? It includes the TCP header only. It does not include the IP header. Okay. So that's what TCP segment means. So it means like you need to include the IP header also. With the IP identification, this is the identification value, and assume that IP header size is 20 bytes. Okay. So basically it will anyway pass through this MTU. Why? Because this MTU is 1500 bytes and you are sending 1420. So it will anyway pass this MTU. So this will be 20 bytes extra here, right? And here you are having 1500 bytes. So you can anyway send this. Further, the packet is allowed to be fragmented, which means DF bit is set to be 0, right? And which of the following option is correct? 2 fragments are created. So at R, how many fragments you will create? So see here, this is P, this is R, this is Q. At P you are getting 1400, and here the MTU is 820. MTU means the data size at the data link layer, which means you need to basically, this is the data size. So 820 bytes can be sit here, and this will be your data link layer frame. Now tell me, if you want to divide this packet, then this packet will be basically 1400 segment size, 20 bytes IP header, right? This is the IP header. Then what you will be doing? You will be basically first subtracting 20 from this, then you will say that 800 bytes of data, IP datagram size. So 800 bytes of the IP datagram size can be sit here, because you need to anyway append the IP header, right? So you need to append the IP header, that's why it will be ultimately 820. So effectively only 800 can carry, this link can carry only 800. So you always need to subtract IP header from MTU minus IP header, always do that. Why? IP header. Why we need to do this? Because MTU is the size at data link layer, okay, and which means this MTU already includes the IP header. That's why to check that how much bytes effectively it can carry, you need to basically subtract the IP header. So this 1400 bytes should be divided into 800, right? 800 and another will be only, I think, 600. So this 1400 should be divided into 800 and 600, and then there will be IP header of 20 plus 20 plus 20. So what they have asked, 2 fragments are created, that is correct, and one size is having 8, one of the size is 820 and another size is 620, right? So 2 fragments are created at R, and the IP datagram size carrying the second fragment is 620. So I think that is correct. So what they have asked, which of the following option is the correct? So 2 fragments are created at R, and the IP datagram size carrying the second fragment is 620. Okay, I think this is correct. If the second fragment is lost, then R will resend the fragment. So if the second fragment is lost, they are saying if the second fragment is lost, see here you are sending 2 fragments. If the second one is lost, then R will resend. So that is false. Why? Because R will not resend, the source will resend, right? So that's why this is false. So this is false. If the second fragment is lost, then P is required to resend the whole TCP segment. So yes, this is correct. Why? Because if any of the fragment lost, then that at the source side we again transmit the whole packet. So that's why C is correct. TCP destination port can be determined by analyzing only the second segment. Okay, this option is important. They are saying that TCP destination. So see here, see when you are dividing this 1400 into 2. So now what you are doing, this is 1400 data and this is your IP header, right? This 20 is your IP header. Now where is your TCP header? TCP header is basically inside this 1400 only, which means maybe 20 bytes, maybe 40 bytes, like that is not given, but that is okay, right? So this TCP header is inside this 1400 only. So when you are dividing into 2, then first packet will be having 20 of TCP, and then I mean the total size will be 800. So 20 of TCP and then 780 here. So the first packet will be having TCP header, second packet won't be having the TCP header. So only the first packet will be having the TCP header, but the IP header will be given to both. IP header is here also 20 bytes, here also 20 bytes. But this TCP header of 20 bytes will be given to only the first packet. Is this okay? Now, the TCP destination port can be determined only by the second packet, no, only by the first packet. If that could have been the option, then the answer is correct. So that's why D is also false. Is this okay to everyone? So if that is okay, then A and C are correct answer here. Okay. Now let's see this question. Consider the three-way handshake mechanism followed by the TCP connection establishment between host P and Q. So P and Q. I think this is easy question. You can do it, but let me just solve it quickly. Let X and be the two random 32-bit starting sequence number chosen by P and Q respectively. So this is saying X as first sequence number. This will say Y. So it will send the SYN packet. If you remember, it will send SYN plus ACK, right? So that's how it happens, and it will send ACK. Suppose P sends a TCP connection request to Q with SYN and the sequence number is X and ACK is 0. Okay. Suppose Q accept the connection request, which of the following is true? So just tell me, whenever Q is sending, SYN should be 1, ACK should be 1, right? So ACK will be 1 to acknowledge that it has received the earlier packet which is having the sequence number X. So what should be the answer? SYN should be 1, and ACK should be 1. So either C or D is the answer. If ACK is 1 and also the ACK number will be x plus 1, so that's why C is the correct answer. See here, ACK is 1, ACK number is x plus 1, and fin is anyway obviously 0, and suitcase number is y because it is starting with y, right? So it is an easy question. I hope that is okay to everyone. Now let's solve the next question. So for the next question, basically I just wanted to give you the glimpse of fragmentation, that how does the fragmentation happen, and then we will be solving the fragmentation questions. Okay, so suppose that you want to send a packet that is having through a network that is having an MTU of 560 bytes. So you want to send a packet, there is a MTU of 576 bytes, and the IP packet has the header of 20 bytes and the data. So basically there is a packet that you want to send from here to, let's suppose here, and it has to pass through this MTU which is 576, and suppose this packet is 1484 bytes, okay, and which is having the 20 bytes header. Now what you need to do, you need to divide this packet into parts so that you can pass through the MTU. So how you will be dividing? See, this is your 1480, right? So if you want to divide that, then you will be dividing it into, basically you will first subtract the 20 from here, and then you will say this is the 556 bytes, right, of IP data it can carry. So you will be dividing this 1484 into 556. So how many packets will be there? If you divide this 1480 into 556, then I think it will be 556 and then 556, and then if you just do it, then it will be 556 plus 556 is 2, 5, 5, 10, and it is 1. So basically it will be 1, 5, 5, 10 and 11. So 11, 12 and 1484. So 11, 12 if you subtract, then it will be 2, it will be 7, 3. So it will be 372, right? It will be 372. So in three packets such that the sizes are this, you will be just dividing. Is this okay to everyone? Now, is this a feasible division? Which means, can you divide like this, or we need to take care of something? See, this is 556. So can you divide into 556? Can you divide into a packet which is having a size of 556? No. Why? Because that number has to be divisible by 8. So if you divide this 556 by 8, then can you divide it evenly? No, right? So you won't be able to divide it. You can quickly check it. If you divide this 556 into 8, then what you will be getting? 566 upon 8, let me just do it. It will be 69.5. So which means you are not able to divide it evenly by 8. And why we need to divide by 8? Because there will be an offset which is basically having a scale of 8. So you cannot divide in 556, that is okay. So what we are going to do, so 556 is effective size because MTU was 576, then you subtracted 20 and then you are getting 556. And there is a 1484 or 1484. So this is a 1484, right? So you need to divide this 1484 such that you are basically having even size. You can divide by the 8 such that you can scale by the 8. So I think instead of 556 you can divide with the 552. So it will be 552 and then the remaining will be I think 380, right? Remaining will be 380, and then you will be having IP header of 2020. So basically this is how you are dividing this packet into 3 packets. Now if I ask you what will be, let's suppose this is your first packet, this is your second packet, this is your third packet or last packet. If I ask you what will the offset, then you will say for the first packet, since it is not following anything, then the first packet the offset is 0. Second packet offset will be this, it is basically following how many data bytes, right? Not including the IP header, only the data bytes. It is following 552 bytes. So basically it will be 552 divided by 8, and then it is following 552 plus 552 divided by 8. So which means 552 by 8 into 2. So this will be I think 69 this will be 128 or 138, and then this will be 0. These are the offset that I have for these 3 packets, right? Now if I ask you other fields, so let me ask you more fragments. What do you think? Will it be 0 or 1 here? So more fragment field here will be, tell me, what will the more fragment field? It will be 1, right? Why? Because there are more fragments that are being followed by that are being followed for this packet. So there are more fragments apart from this. So it will say yes, and it will say no, this is the last fragment. So MF is 0 means this is the last fragment, right? So I hope that is okay to everyone. Now if I ask you another fields, if I ask you what is the total length, so what will the total length of first packet? Let me just write the total length here only. So these are the 3 packets that we have. So what will the total length of the first packet? Total length is basically, you just need to add 20, right? So yeah, you can just add 20, which means the total length will be 5, here 572, here it is 572, here it is 400, right? So this is the total length in the IP header. So these are the fields of IP header. And now what other fields we can have? Header length will be just 5 in every case, because we need to divide by 4. So header length will be anyway 5. So these are the fields that we have, right? I hope you got it. Now let me know if there is any doubt here. So basically what we did, we have divided this 1484. We have divided this 1484 into 3 packets, right? 1, 2, 3, such that it is 552. This is 552. And then this is 380, and then you have 20 bytes of IP header each. This is 20, this is 20, this is also 20. Now suppose if I extend this question further, and suppose if I say that there is a MTU, so basically like you are passing this to a MTU of 576, right? This is MTU 576. Then that's why you need to divide this into 3 packets. Now at here you will be having 3 packets, these 3 packets, right? These 3 packets will be at this router. Now suppose here also, if you want to send it to some other router, then there is some MTU of, let's suppose 500 MTU. Okay, let's suppose 500 MTU. MTU is 500. Then how you are further going to divide it? So what you are going to do? This will not be divided. This will be divided. This 552 will be divided, right? So this 552 will be again be divided, and then this 552 will again be divided. Now this 552 will be divided into 480 and then 20, because the MTU is 500, which means the 480 is effective data it can carry. So 480 and 20, sorry, 480 and not 20, it is 72, right? 480 and 72. This 552 will be divided into 480 and 72. Similarly here 480 and 72, and then this will be as it is, which means this is just 380, right? So if I am not writing the IP header, if you want you can write it, which is 20 bytes. Is this okay to everyone? Now write all the fields. Tell me more fragments. What will the more fragments? So this is the packet number 1, this is packet number 2, packet number 3, packet number 4, packet number 5. So packet number 1, packet number 2, packet number 3, packet number 4, packet number 5. Tell me more fragment fields. So the more fragment here is 1, because it is following more fragment, more fragment, more fragment, more fragment, and then more fragment is 0. Right? What is the offset? What will the offset? Offset here is 0. Here offset will be 480 divided by 8. Here offset will be again 69, because 552 divided by 8, which is again 69. Here again the offset will be like 552 plus 480 divided by 8. So this is like if you divide the 480 by 8, then how much you will be getting? This is 60, right? Then basically here the offset will be 69 plus 60, which is 129. So here the offset will be 129, and here the offset will be 129 plus 72 by 8. So here the offset will be like you can calculate it. So basically 129 plus 72 by 8. So this is how the offset will be. So basically it will be 138, I think, right? 138. So these are the offsets. See, the offset is not changing. Earlier also offset for this last package was 138. Now also offset for the last packet is 138, right? So these offsets are not changing. But if you are dividing, then some of the offset and some of the fields of other packets are changing, right? I hope that is okay to everyone. Let me know if there is any doubt. So what other fields that we have? We have offset, we have more fragment, and yeah, and you can also calculate the total length. Total length will be you can just add 20 here. So for every size you can just add 20, right? Okay, so M blaster is giving me the answer, which is 0, 60, 69, 129 and 138. 0, 60, 69, 129, 138, right? That's correct. Now can anyone tell me how we are going to reassemble them? How we are going to reassemble them at the source? So these are the offsets that we have. Then how I am going to reassemble? So what will be the reassembly algorithm? What I am going to do? I am going to check for the SAM identification number. For one identification number, for only SAM identification number. For SAM identification number, we are going to do this procedure. What we are going to set, we are going to say, okay, let's say the offset is one variable, which is 0, and then we are going to search for the offset 0, right? We are going to search for the first packet, which is offset 0. Then we will search for the second packet, which is having the offset 60. So we will search for offset, which is currently 0. And then we will, once we find a packet which is having offset 0, then we will basically update the offset equal to offset plus your number of data bytes by 8, right? Number of data bytes by 8, which means if this is having offset 0, then I will calculate the next offset using this. Using this I will calculate the next offset. Now this offset will be updated to 60. Now I will be searching for the 60. Right, which means I am searching for the next packet. Now once I get this packet, I will be searching for, once I get this packet using the 72, I will be updating the 62 what 69, right? So using the 72, I will be saying the 60 plus 72 by 8, which means 69. Now I am searching for the 69. Now similarly I will search for the 129, and then similarly I will search for the 138, and I will repeat it. I will repeat it till more fragment is 1, right? Sorry, more fragment is 0. More fragment is 0. So I will keep on repeating this. I will keep on searching for the offsets till the more fragment is 0, right? I hope that is fine with everyone. So I will be keep on searching for the offset till the more fragment bit is 0. That's how the reassembly works. Okay. Now let's get back to some new questions. Now this is the question from distance vector routing algorithm. Now suppose so basically this is a linked question, which means this description is given to you, and then there are two questions for this question. Okay, there are two questions they have asked from this description. So I have basically written the description on the next page just to zoom it out. So just read out this description and let's solve this question for the distance vector routing algorithm. What they are saying, that consider there are 5 nodes that are N1 to N5. Okay, the network uses the distance vector routing protocol. Once the routing has been stabilized, then distance vectors at the different nodes are given as follows. So they have given the distance vectors to us. Okay, now each distance vector is a distance of the best known path at that instance to other nodes. So which is N2 to N5, where the distance to itself is 0. So which means this distance vector is saying that N1 to N1 distance is 0, N1 to N2 distance is 1, and N1 to N3 distance is 7, N1 to N4 distance is 8, and so on, right? Sandeep is asking, sir, isn't offset numbers stored at the destination to avoid searching in the array? So I'm not getting, so offset how they can, okay, no, there could be multiple paths, right? So Sandeep, there could be multiple path. There need not to be only the single path they are following. So there could be multiple MTUs, there could be multiple paths, and there could be multiple, like there might be some changes in the network and the MTU might get changed. So these are generally not stored. Okay. So let's solve this question. Consider a network. So okay, we are here that we are saying that each vector is consisting each node is consisting a vector of the distances. Also all links are symmetric and the cost is identical in the both the direction. In each round, so now just listen here carefully, they have defined as round, they have defined something as round. In each round, all nodes exchange their distance vector with their respective neighbors. So they are calling it as a round. In each round, they are basically exchanging their vectors. So I will say that this is one round if n3 is exchanging its vector to n2 and n4, right? So I will say this is an round. Then all the nodes update their distance vector. So this is how they have defined as a round. In each round this is happening. This is how they have defined as a round. Okay. Now in between two rounds, any change in the cost of link will cause the two incident nodes to change only that entry in the distance vector. Now what they are saying, in between two rounds, which means that if n1 is sharing its vector to n2 or n2 is sharing its vector to n1, so this is called one round, and there will be another round after some time. So in between two rounds, let's suppose this link or any other link get changed to something. Let's suppose this link is getting changed to 2, suppose. Then this change will be a local, which means they are not considering as a round. They are saying that in between two rounds, okay, any change will cause two incident nodes to change only that entry, which means if this link has corresponded to 2, then n1 will update that, okay, n1 to n1 is 0 anyway, n1 will update that now from 1 I have changed to this 2, and this is not a round. Okay, this is not a round, this is in between any round. I hope that is okay to everyone. So they are saying in between any round, then they are defining like this. Now they have asked some question. The cost of link n2 to n3 has been reduced to 2 in both the directions. After the next round of updates, what will be the new distance vector to n3? So they are saying the n2 to n3, this distance has been updated to 2. So let me just update this to 2. Okay, they are saying this has been updated to 2. Now tell me, if this has been updated to 2, what will happen immediately? So immediately n3 will change that, okay, n3 will say that this is to n1, and then n3 will say that earlier it was 6 to n2, now it has been changed to 2. This is the vector of n3, isn't it? Similarly, what will n2 say? N2 will say that to n3, see, this is to n1 something, and then this is to n2, which is 0, and to n3 earlier it was 6, then it will also update to 2. And this is not they are considering as a round. They are saying this is the immediate effect that is happening in between the rounds. Now once this happens, then after next round of updates, what will be the distance vector at n3? So n3 will be getting the distance vector from n4 and from n2. So tell me what n3 will be getting from n4 and what n3 will be getting from n2. From n4 it will be getting the as it is, because there is no change, which means it will be getting 87204, right? And then from n2 what it will be getting? It will be getting 1 0, instead of 6 it will be getting 273, isn't it? So at n3 I will be getting these two vectors, and then n3 to n4 is already 2 and n3 to n2 is now 2, right? So basically I just need to compute the final vector for n3. What it will be? From like to n1 it will be saying this is reaching in 1 plus 2, which is 3, and this is reaching in 10, so 3, and then n3 will be saying to n2, if I want to go to n2, this is reaching in 2, this is reaching in 9, so this is just 2. From n3 to n3 it is 0. From n3 to n4 it is just 2 and it is 9, so obviously 2, and then it will say 6 and 5, so it is 5. So 32025. 32025. So that's why A is the correct answer, right? Okay, I hope you got it. So just observe the question, what they are saying. They are saying about the next round, right? So in the next round, the n3 will be getting the vectors from n4 and n2, and then using these two vectors, you just need to calculate the n3 vector, right? That is what you need to do in this question. Now let's solve the linked question, which is the next question. In the next question, what they're saying, after the update in the previous question, the link n1 to n2 goes down. So they are saying after the update in the previous question, which means that once this 6 goes to 2, now n3 will update, right? N3 will update its vector, which is this. Similarly, not only n3, every other vector will update, right? Every other node will update. So let me copy this. See, not only n3, every other vector will update. So which means not only just n3 will say that its vector is 3 to 0 to 5. Every other vector will update to something, right? So which they have not asked, but anyway, like every other vector will update. So n3 vector is, we have calculated 3 to 0 to 5. Now similarly, every other vector will get updated. Now what they are saying, that n1 to n2 link goes down. So this link goes to infinity. Goes down means goes to infinity. And now n2 will reflect this change immediately in its distance vector. Now n2 distance vector will be having distance to n1 is as infinity. Similarly, n1 distance vector will be having distance to n2 is as infinity, right? So that's what is happening immediately. I mean, they are not waiting for the next round. They are not waiting for that to happen for the next round or anything. That is happening immediately. So if there is any change, that get reflected immediately. In earlier question also, this change 6 from 2, that I am reflecting immediately without waiting for the round, right? That's what given in the description actually. So I am not making any assumption. That's what given in the description. And now after the next round of update, what will the cost to n1 in the distance vector of n3? So they are saying in the distance vector of n3, what will the cost to n1? So they are asking this entry if after the next round of update. Now n3 will be getting entries from n4 and n2, right? So n3 at n3 I will be getting from n4 and n2, and then I will be getting a vector from n4. I will be getting a vector from n2. Now what vector I will be getting from n4? So there will be, like, I need to calculate actually that vector. Why? Because from earlier question I just calculated n3 vector. I first need to calculate all the vectors, then I need to change this 1 to infinity, then I need to calculate the n3 vector. You are getting the steps? See, they are saying in the previous update, in the previous question, the link n1 to n2 goes down after the update in the previous question, which means you need to update all the vectors, not just n3. You need to update n4, you need to update n5, you need to update n2, you need to update n1. You need to update all the vectors, and then this 1 will go to infinity, and then they are asking the n3 vector, right? I hope the sequence is clear to everyone. So let me do one thing. Let me not update all the vectors, because my answer is relying on only n4 and n2, right? So let me just focus on these two vectors, n4 and n2. Is this okay to everyone? See, in the previous question, which means in this question number 52, I am just focusing on n4 and n2, because in the question number 53, whatever they are asking is actually depending on n4 and n2 only, right? So I hope that is okay. So I am just focusing on n4 and n2. Now they are asking about what will the cost to n1 in the vector of n3. They are only asking about the vector of n3, this entry, n1 entry. So which means instead of just focusing on two vectors, I will be just focusing two entries of these two vectors, because ultimately they are asking this, right? So that will depend on this entry and this entry. So let me not focus on the whole these two vectors. Let me only focus on this entry and this entry, right? So what will this entry? This entry will depend on n5 and n3. So n5 will say 4 and n3 will say 7. So n5 and n5 will say 4, n3 will say 7. Now this is at n4. At n4 we have this. So n4 to n5 is already 4, and n4 to n3, is this visible to everyone? So I hope that is visible. So n4 to n3 is already 2. So you will say that 8, right? So you will just update that to 8, which means 8 is already there. So basically you will be getting 8. You will be getting this entry as 8, and similarly you will be getting some entry from n2. And since this has been updated to infinity, so you will be getting infinity. So this will be 8, you will be getting here, you will be getting infinity here, right? You will be getting infinity here. So tell me which is minimum, 8 or infinity? 8 is minimum, right? So anyway, n3 to n4 is already 2. n3 to n4 is already 2 and you are getting 8, right? So which means you will be updating that to 10. 8 plus 2, 10. So which is the correct answer? C is the correct answer, right? I hope that is okay. So that is why C is the answer. So you just need to read the description carefully. That is all. Now let's solve some questions regarding the TCP. So this question is saying, let the size of congestion window of a TCP connection to be 32 kilobytes, right? So the size of congestion window, they are saying 32 kilobytes, and they have given the maximum segment size to be 2 kilobytes. So basically, if I write the congestion window size in the maximum segment size, then it will be 16 MSS. It will be 16 MSS. Is this okay? Because the 32 bytes they have given as a size of congestion window, and 2 kilobytes, 32 kilobytes they have given as a size of congestion window, and 2 kilobytes they have given as a size of maximum segment size. So that is why if I write the congestion window in the maximum segment size unit, then it will be 16 MSS. Okay. Okay. Now let's read further. Now what they are saying, the round trip time is given to be 100 milliseconds, right? Round trip time is given to like this, and the time taken by the TCP connection to get back. Okay, round trip time is this, and they are saying something, I think. Okay, the size of congestion window is this, and when the timeout occurs, so there is a timeout. Now if you remember that there are two phases, one is slow start, another one is congestion avoidance. Do you remember it? Now it depends on the implementation. That, see, let's suppose there is no timeout or no 3 ACKs. Okay, then if the things are very normal, then it will enter into the congestion avoidance whenever your threshold is getting increased, which means let's suppose this is your threshold, and then congestion window size, or the sender window size, basically the sender window size is greater than the threshold. The window size is greater than the threshold, then you will automatically enter from slow start to congestion avoidance. Is this okay to everyone? Right? This is what you do if there is a congestion. So if your congestion window size is greater than or equal to threshold, right? Now suppose that there is a timeout in the slow start phase. Okay, so there are two conditions that can happen. Either there will be a timeout or there will be a 3 ACK. So let me write on the next page. So basically, let's suppose this is slow start and this is congestion avoidance. Okay, and if your congestion window size increases your threshold, then you will automatically go here, right? And this is how you are starting, and there is no error, which means there is no timeout or there is no 3 ACKs, right? Now suppose that there is a timeout, so there are two events, either timeout can occur or there may be 3 ACKs, right? Now tell me, if there is a timeout here, then what you are going to do? You are actually going to be here only. If there is a timeout, then you will say that your threshold will be now the half of your congestion window. So your threshold will be half of congestion window, CWND, right? If there is a timeout here, and your congestion window size, you will update that to be 1. Is this okay to everyone? What if there is a 3 ACKs here in the slow start? Then what will you do? So basically it depends on the implementation. I mean, some implementation does not care about timeout or 3 ACKs. So some implementation says either this is 3 ACK or this is timeout. I am going to do the same thing here. Okay. Similarly, here also either this is 3 ACK or timeout, I will go here. Or timeout, I will go here and I will update my threshold to half of congestion window, and then congestion window size will be 1. So this is the implementation 1. I mean, there might be multiple implementations, and this is one of the implementation which is valid implementation. Okay, so this is implementation 1. So in this implementation, what I'm saying, that I do not care whether there is a 3ACK or timeout, whether there is a 3ACK or timeout. I am treating both of them as a same. Okay, as same. Now there is a second implementation. Let me write it here, implementation 2. In this implementation, I say that suppose there is a slow start here and there is a congestion avoidance here, congestion avoidance. Okay, I'm not writing it fully, but CA means congestion avoidance. Now it says that if your congestion window size CWND is basically greater than or equal to your threshold, your slow start threshold, then anyway you will go to the congestion avoidance. Here also I was doing the same thing, but in this implementation, I am basically differentiating between timeout and the 3ACKs. How? I will say if there are 3 ACKs here, then I will go to the congestion avoidance. If there are 3 ACKs. Okay. Similarly, if there are 3 ACKs here, then I will remain in the congestion avoidance and I will update my parameters. So what are the parameters that I need to update? In case of 3 ACKs, I will say that my slow start threshold is just half of my congestion window, and my new congestion window is my basically window size is basically half, which means it is just threshold. So this is how I am going to update, right? Similarly here. So basically in case of 3 ACKs, I am always going to the congestion avoidance phase, but in case of timeout, I am going to the slow start. So if there is a timeout here, then I will go to the slow start. Similarly, if there is timeout here, then I will go to the slow start. And in case of timeout, I will say my congestion window size is 1, right? And my threshold will be half of my window, right? So basically, in case of timeout, I always go to the slow start phase, right? In both of the implementation. In case of timeout, I always go to the slow start phase. So basically some implementation does not differentiate between 3 ACK or timeout, and they always go to the slow start. Okay, some implementation says that if there is a 3 ACK, then I do not need to go to the slow start. I can go to the I do not need to start with the 1 MSS. So I can go to the congestion avoidance directly with my congestion window size like this. Congestion window size to be a threshold. Okay, so what they have asked in this question, they are saying that timeout has been occurred. So in case of timeout, I will always go to the slow start. So which means my congestion window size will be starting from 1. So if there is a timeout, then my congestion window size will be just 1. I do not care whether I am like which implementation I am using, either implementation 1 or implementation 2. In case of timeout, I will always go for congestion window size will get updated to 1. So it is 1, and then it will be 2, then it will be 4. What will be my threshold? Threshold will be 8 MSS. Why? Because my congestion window size will threshold will be current congestion window size divided by 2, right? Current congestion window size divided by 2, and my congestion window size will be updated to 1 MSS. So basically 1, 2, 4, and then it will be 8, then it will be 9, 10, 11, 12, 13, 14, 15, 16. Now from 1 to 2, right? From 1 to 2 congestion window, you are taking 1 RTT. So 1 RTT here, 1 RTT here. So just count it: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you are taking 11 RTTs, right? 1 RTT is having 100 milliseconds, so that's why your answer should be 1100 milliseconds, right? So congestion control is very confusing. M Blaster is saying. No, these are Ashish. These are not Reno implementation. So basically, there are different implementation. So I think this is none of them. So basically, Reno implementation is, I think, a little more smarter than this implementation too. Okay. So these are just two implementation I am showing you, and these need not to be practically implemented. So practically whatever we are implementing, there is one more block, that is apart from the slow start and congestion avoidance, I do have one more phase basically, and this oscillates between three phases practically. Okay, so neither this implementation 1 or not this implementation 2 get implemented practically, but you don't need to take care of that. You do not need to worry about it. Okay, otherwise there are many implementations. So let's solve this question. In this question what we are saying, that on a TCP connection, current congestion window size is 4 kb. The window advertised by the receiver is 6 kb. Okay, so current congestion window they are saying is 4 kb, and the receiver is advertising the window to be 6 kb. Then, so basically receiver is saying you can send me till 6 kb, and currently I am having the congestion window to be 4 kb. So which means the sender window will be minimum of congestion window and receiver window, right? Whatever receiver is advertising. So sender cannot send more than 4 kb, because congestion window is just 4 kb and receiver window is 6 kb. So that's why it cannot send more than 4 kb. That's why 4 kb should be your sender window size. So the current window size should be 4 kb, which means B should be the answer. But what they have given, the last byte sent by the sender is 10240. So see, the sender window size is 4 kb, which means this means 4 into kilo means 1024, which means 4096 bytes. So sender is having 4096 bytes, right? So answer is B, but I am just making use of other information that is given to us. Ashish, official implementation last time part. Okay, last TCP timing you are saying. Okay, I will explain that in the next video. Okay. So I have on the Go classes, I have updated the PDF to read out. So there's a one-page PDF only, but if you want, I can explain. So this is basically 4096 bytes. This is the sender window size, right? Now they are saying the last byte sent is 10240, and the last byte acknowledged by the receiver is this. So basically receiver has acknowledged till this bytes. So this is 8192 suppose. So receiver, let's suppose, has acknowledged these much bytes, and the last byte sent, I have sent till this point. So this point is basically 10240. So I have sent till this point, but receiver has acknowledged till this point only. Which means, what can I say? Let me write it here. What can I say? That byte number 8193 to 10240 are sent but not acknowledged, right? So these byte numbers are sent, but these byte numbers are not acknowledged yet, right? And this byte number from 1041, so this will be 10241, from this to, so there will be, see, this size total has to be 4096, because the sender window size is 4096. If this is acknowledged, so if you just calculate it, then it will be 1041. So you actually need to calculate it. Let me just calculate it. It is 8193 plus 4096 minus 1. So it will be 12288. So 1041 to 12288. Right, this is your current sender window, right? You are getting it? This is your current sender window, because sender window size is again 4096. Sender window size is 4096. So that's your current sender window. So sender has sent this much, and sender is waiting for this to be acknowledged, and sender has not sent this much. So this is sent but not acknowledged, or this is not at all sent. Not at all sent. Maybe because why it is not sent? Can anyone tell me why it is not sent? Maybe because the data has not been come from the application layer itself, right? That's why it may not be this may not be have been sent till now. So maybe waiting for the data, maybe this data waiting, this data in the waiting from application layer, right? Maybe sender is waiting from the application layer to fill this data. But anyway, they have asked the sender window size, the current window size, which is just 4096. I was just making use of other information that is given to us. Okay. So now let's solve this question. This question has been asked in GATE 2021. I think this is an easy question. You can do it. Like this is very theoretical question and very easy question. So you can do it. If there is any problem, you can ask me. So I am skipping this question because this is very easy question. Okay. Now let's move to the next question. Consider IP network ABC, where HA in the network A sends a message each containing 180 bytes of data to HC. So basically here you are sending 180 bytes of application data, which means here you need to add the TCP or UDP header and then IP header and these things, right? So you need to add the TCP and IP header. So this is just application data. So it wants to send to C. This passes through the intermediate network like this, including 20 bytes of header. Okay. So in this 180 you need to add, other headers, which means TCP headers, IP header, like that, right? IP header and so on. So what they are saying, in each network, so maximum packet size is, the maximum packet size including IP header. So basically maximum packet size including IP header they have given. Then what does this mean? These are the MTUs. So these are the MTUs for each network. So 1000 is MTU for network A because this is including IP header. That's why these are the MTUs, right? Now 100 is basically bottleneck. 100 is MTU of this, which means it can send effectively 80 byte of data only, 80 byte effectively, right? So apart from the IP header, it can send 80 bytes. Okay, it can pass through the 80 bytes. Now there are some bandwidth that are given, like this is the bandwidth they have given. Assuming that the packets are correctly delivered, how many bytes including the header are delivered to IP layer at the destination of one application message in the best case? So they are saying that like including the IP header, so basically at the IP layer, which means at the IP layer, basically they are asking at the IP layer how many bytes how many bytes have been delivered to the C. So basically we are sending 180 bytes, but because of the fragmentation I may need to send more bytes, right? So see here we are sending 180 bytes and there is a MTU of 100 here, which is a bottleneck, right? So we are sending 180 bytes. There is a packet of 180 plus 20 because 20 is TCP header and then IP header of 20. So what I will be doing, I will be dividing this into 80, right? Because effectively it can send 80 only. So basically this is a 200 bytes of data that I need to divide into 80. So 80 and then 80 and then 80 and then 40, right? So there will be 3 packets in which I will be dividing it. So 20, obviously 20 bytes of IP header I need to append 20 bytes of IP header at each fragment. I need to append 20 bytes. So total I will be sending how many bytes? This is 100, this is 100, this is 60. So I am sending 260 bytes. Now do I need to again fragment it? No, because this MTU is again 1000. So here I am having MTU of 1000. So I do not need to again fragment it. So only one time I need to fragment it. So 260 bytes of data including the 60 bytes of IP. So in this 260 I have 60 bytes at the just IP and they are asking at the IP layer. So at the IP layer I will be receiving 260 bytes, right? 260 bytes. So that's why D is the correct answer. So I am sending 180 bytes and I am receiving ultimately, sorry, I am sending basically 180 plus 20. I am sending 200 bytes here including the IP headers and here I am receiving how much? 260, right? Including the IP headers. Is this okay? Okay, so D is the correct answer. Now that question is linked question, so I do have other parts also. So in this part they are saying that what is the rate at which the application data is transferred. So they are saying what is the rate. So on what rate we are sending the data. So how much data we are sending basically? We are sending 260 bytes, right? So they are asking what is the rate at which the application data is transferred. Okay, so what will be the time to transfer 260 bytes? So tell me what is the time to transfer 260 bytes from B to C, from B to C. It will be length upon bandwidth, so which is 260 bytes, like if you convert that to bits, upon 512 into 1000. So basically if you calculate it, it will be some number, right? So I think that will be 65 upon 16,000. So these like these many seconds you will be taking, right? These many seconds for 260 bytes from B to C. And then what they have asked? They have asked that what is the rate at which you are sending the data. So basically this B is only the bottleneck, right? At B you are sending 260 bytes in 65 upon 1600. If you further solve it, then it will be 13 upon 3200, right? 13 upon 3200 seconds. In 260 bytes you are sending in this much seconds. So what is the rate? You need to send how many bytes? 180 bytes, right? Effectively at application data you have 180 bytes. So basically 180 bytes you will be sending in 1 upon 13 into 3200 into 260 into 180, right? So you need to calculate this number. And so okay, so 260 bytes you are sending in this much time you are sending, and you want to send 180 bytes. Okay, if there won't be a unitary method, I think. See, you are sending 260 bytes. Let me write it here. So this number will come out to be 13 upon 3200, right? So this much time you are taking, right? So total time you are taking, time taken is 13 upon 3200 seconds. This much time you are taking to send how many bytes? 180 bytes, right? To send just 180 bytes, because 180 byte is your application data. So to send 180 bytes. So that's why your rate will be how many bytes you are sending upon how much time you are taking, which is like this. So you can calculate this number and there will be the final answer based on this. So I think the answer was B. So that's why like this number will come out to be 354.46 kbps. So I think that is okay, right? So basically the data rate will only depend on the bottleneck. So bottleneck is this. That's why I am calculating for the B only. So data rate will only depend on the bottleneck. Okay. See what they're asking. They're asking is that what is the rate at which the application data is getting transmitted to SC. So basically you need to find which is the bottleneck, which means like either the rate. So if you calculate the rate here, then the rate will be how much data you are sending. You are sending 180 bytes, right? And you are sending with the bandwidth of 1 Mbps. So if you calculate the rate here, it will be 180 upon some 1 Mbps, which means 1 into 10 power 6, right? So this will be lesser than this number. This will be lesser than this number into 8. If you calculate it, then this, okay, this is 1 Mbps and this is 512 kbps. Yeah, right. So this will be lesser than this number. So basically the bottleneck is only at B. So what I'm going to do, I'm going to take care of the B only, which means if I calculate the data rate at B, then I will be able to tell the bottleneck bit data rate. So that's why what I did, I just calculated what is the data rate at B. So 260 bytes I'm sending from B to C, which means I'm taking this much time to send from this 260 bytes to send these 260 bytes from B to C, right? To transmit these 260 bytes. So basically this is the bottleneck data rate, right? This is the time I am taking, and effectively I am sending just 180 bytes. Okay, so that is why this will be the bottleneck data rate at B. Okay, let me know if there is any doubt. We have one last question. Before that, let me know if there is any doubt. Or otherwise, what you can do, you can just go through this question once again, because this is one tricky question, and then you can again let me know, okay, in the next class. So we are going to have one more revision class of CN. So in that also you can let me know. So let's solve this last question. In an IPv4 datagram, the M bit is 0 and the header length is 10. If the header length is 10, then what does this mean? What will the header length, actual header length? It will be 40, right? You got it? Why? Because 10 into 4 you need to do 10 into 4. That's how you will be calculating the actual header length. So it will be 40. Then what they have said, the total length is 400. So the total length is 400 and the header length is 40, which means 360 is your data. And the fragment offset value for this packet, the fragment offset value is 300, which means 300 into 8, which means 2400 bytes of data are, so 2400 bytes of data is basically before it. Okay, that is apart from the IP headers. The position of the datagram, the sequence number of the first and the last bit of the payload respectively are. So if that's the case and M bit is 0 here, so M bit is 0, which means this is the last fragment, right? This is the last fragment, so either A is the answer, C is the answer, and the sequence number. So the sequence number of the first and last byte. So if you ask me what will the first byte here, so it is following 2400 bytes. So that's why 2400 will be the first byte sequence number, right? First byte sequence number will be 2400, and then you need to add how many bytes here? 359. Why? Because this is 360 length. So that's why 2400 plus 360 minus 1 you need to do, and if you do that you will be getting 2759. So basically the last byte number will be 2759, right? So that is why C is the correct answer. Okay, so I think, okay, there is one more question that we have, and this question is also easy. If you want, I can solve it. Otherwise, you can solve this question. This question is also easy. So basically, in the next video, we will be covering all the topics of CN which we have not covered. So I mean, apart from TCP/IP, so this is TCP and IP or distance vector routing. So these are the protocols that we have covered, and also we have covered a little bit of sliding window, right? So these are actually most frequent topics that they ask. In the next video, we will be covering other topics, okay, whichever have been left. Okay, thank you for watching. Let me know if there is any doubt. Okay then, thank you everyone. Good night.